Welcome to this maths made easy video on applications of differentiation. And to start with, let's take a look at finding maximum and minimum values of volume and area. We can use differentiation to find optimal values of dimensions of objects. So let's say the wish here is to create a hollow box of length 2x, width x and height h. We have a limit of 600 centimeters squared, of wood to use. So to find the maximum volume possible, we must find two equations in volume and area. So the volume here, if we just note the dimensions again, so we have length here L of 2x, we have a width here of w, which is equal to x, and a height here h, which we'll just say is equal to h. So now the volume here is simply length times width times height. So that's 2x times x times height. So in that case we get 2x squared h. And the area then, A, that would simply be two lots of 2x times x. So that's two lots of 2x times x plus two lots of 2x times h. And finally, two lots of x times h. And if we simplify here, collect like terms, what we obtain then is 4x squared plus 6xh. And this is equal to 600. That's our constraint, essentially, our limit of 600 centimeters squared of wood to use. Now, of course, we only want to differentiate in terms of one variable. So what we'll do here is transform the second equation to h equals. So here h equals 300 minus 2x squared over 3x here. So we've just rearranged this equation here to be in terms of h. And what we can do with this then is plug this back into our equation here for the volume. So therefore, v here is equal to 2x squared times h, where h is equal to this expression. So that's 300 minus 2x squared all over 3x. So here, if we simplify this, what we get is 200x minus 4x cubed over 3. So now we can differentiate with respect to x to find the maximum volume of the box. So if we differentiate here with respect to x, so therefore we get dv by dx. And in that case, that would give us 200 here. Again, going term by term, so we get 200 and minus 4x cubed over 3. Well, what would that give us here? Well, that's going to give us minus 4x squared. So minus 4x squared. And what we do here is we set this equal to 0. And now, if we solve for x, so if we solve for x here, what we find then is 4x squared is equal to 200. Divide by the 4, we get x squared equals 50. So x squared equals 50. So therefore, x must be equal to the square root of 50. And clearly we can only have the positive solution here, as we're talking about dimensions. So that just gives us x equals the square root of 50. But we must also verify that this is a maximum rather than a minimum. So now we need to find the second derivative. So we've run out of room here, so I'll just take note here before we clear the screen. So now, like we just said there, we're going to find the second derivative. So if we find the second derivative here, what would we get? Well, the second derivative here would simply be equal to minus ax. So if we substitute our solution in then of x equals the square root of 50, what that gives us is minus a times the square root of 50. And clearly, this is less than 0. So this is definitely a maximum point. So therefore, this is a maximum point. So that's a maximum point. So therefore, we have x equals the square root of 50. So x equals the square root of 50. And h, if we just substitute our value in here of x, is equal to 200 divided by 3 times the square root of 50. So therefore, v max here is simply equal to 20,000 divided by 3 times root 50 there. Okay, so 20,000 divided by 3 root 50. Okay, so that gives us everything we need there for finding maximum and minimum values of volume and area. And finally, let's take a look then at finding rates of change in mechanics. In mechanics, we'll talk about the derivation of acceleration and velocity from displacement. So from the displacement s, we can differentiate with respect to t to find v. And we differentiate again to find the acceleration a. So here we can say the derivative of s here, the displacement, with respect to t, time, is equal to v. And therefore, if we find the second derivative here, so the second derivative, that gives us dv by dt, and that's equal to the acceleration like we've already stated. So for example, let's say we have an equation for the displacement here, s equals, let's say 2t cubed, so 2t cubed minus 3t squared minus 4t plus 1. Okay, so let's just clear this at the front. Okay, so that's our equation there for displacement. Now we can find an equation for the velocity. So therefore the velocity here is found by differentiating s here with respect to t. So ds by dt is equal to v, which is equal, so if we differentiate term by term here, differentiating 2t cubed with respect to t would give us 6t squared. If we differentiate minus 3t squared with respect to t, that would give us minus 6t. And finally, if we differentiate minus 4t, that will give us minus 4 there. Okay, so that gives us v there, the velocity. And in that case, if we want an equation for the acceleration, then we would just differentiate here one more time with respect to t. So therefore, the second derivative is equal to a, and again, just differentiating here term by term, that would give us 12t minus 6 there. Okay, so therefore, we can find the values of t such that v equals 0. All we do here is we set v equal to 0. So that tells us 6t squared minus 6t minus 4 equals 0. And this must have solutions at t equals a half plus or minus the square root of 11 over 12. But clearly we can't have a negative time value. So in that case, we only obtain one solution here, and that is t equals a half plus the square root of 11 over 12 there. Okay, so in that case then, if we just finish this off with a different pen colour, we can find a then. So a is equal to 12 times this value of t here, so that's a half plus the square root of 11 over 12, and don't forget we minus the 6 here. Okay, and in that case, if we just evaluate this on our calculator, we get 11.49 there. Okay, and that gives us the value of the acceleration. So we can conclude that this is a point of minimum displacement. So that gives us everything we need there for finding rates of change in mechanics, and that concludes this mass media video on applications of differentiation.